Yes, now we'll go to the next thing, collector to base bias. The third variation of the biasing circuit is collector to base bias. Can anybody say what change we have done to the circuit from the previous circuits? See the circuit diagram and say what is the change. What is the change we have done to this circuit? Something should be changed, right? What is that? Usually RB will be connected here to VCC, but see here where RB is connected. RB is connected to the collector here. So that is why it is called as collector to base bias, because the base resistance is coming from collector to base. Okay, so it is called as collector to base bias. Very simple biasing techniques, and it is going to provide a good stabilization of your Q point. See, first bias is fixed bias, where you will not have any RE, you will have RB and RC connected to VCC. Next one, emitter bias. Emitter bias is same fixed bias plus an emitter resistance RE. Collector to base bias is say a form of the first bias, fixed bias, but see where your RB is connected. RB is connected at the collector terminal, not at the VCC. So these small changes, if you do, we are finding a good result in the stability factors. So a stability factor is going to reduce a huge way for us in that case. Okay. So see, if the collector current is going to increase with temperature, or the transistor is replaced with the higher beta, this resistance RB will act like a feedback. So usually for common emitter amplifier, input is base, output is collector. So anything connected between input and output is called as the feedback resistor. So this feedback is used for controlling the current of your transistor. What happens if collector current is going to increase or decrease, this base current will adjust accordingly to maintain the constant Q point. When IB is going to increase, IB will decrease to ensure that when IB is decreasing, this IC also will start dropping. So it is just like a feedback action, right? So whatever variation IC you are going to have, you are going to have an opposite variation in IB, because you see here the current is splitting. So if IC is going to increase, more amount will be entering your collector. Definitely IB will less, IB will reduce. When IB is reducing, IC will reduce, because IB equal to beta into IC equal to beta into IB, right? So if IB is reducing, IC will also reduce. So it is just like a feedback action which happens repeatedly to ensure that your IC does not vary too much. So indirectly, for any change in IC, my stability is assured. My Q point is fixed. So this gives a very good solution when your IC is going to vary with temperature. The IC will change only with temperature, right? So that variation of IC is tackled beautifully in this collector to base